now that we're thinking about reaction mechanisms, one of the things that we can think about is how does this relate to systems where we're going to deal with equilibrium happening in our reactions. So let's look at a simple case where we have our molecules A and B, and we have a simple reaction mechanism, or an elementary step, where we have a forward reaction to molecule C plus D, and those molecules C plus D can react to form A and B, right? So we can have a forward and a reverse rate. And so for each, since these are elementary steps, we can write the rate law for the forward and reverse reactions. So for the forward reaction, our rate is equal to K1 times concentration of A times concentration of B. And V minus 1, the rate for the reverse reaction, is equal to K minus 1 times concentration of C times concentration of D. Now, when we're thinking about eventually the system, if we leave it long enough, will reach equilibrium. And as we've already expressed previously, we know that at equilibrium, the forward and reverse rates have to be equal. We talked about that in the last chapter. So we know that at equilibrium, V1 has to equal V minus 1. Or else if it didn't, then the system wouldn't be at equilibrium. So we can go ahead and plug in our definitions here. So that gives us K1 times A at equilibrium times B at equilibrium will be equal to K minus 1 times C at equilibrium times D at equilibrium. Now we can go ahead and rearrange this and put the K's on one side and the concentrations on the other, the equilibrium concentrations. And what we'll see is we get K1 over K minus 1 is equal to, let me make sure I get C's will be on top, C and D, concentrations at equilibrium. So our products will be on the top, and our reactants will be on the bottom. And what you may recognize, though, is that what we have on the right here, products over reactants, this is an equilibrium constant. So this is equal to Kc. So this gives us a way to relate our equilibrium constant to the rates of our elementary steps that are happening in the reaction. And so this is something that we've seen previously, but this is a useful tool. So this only applies specifically to elementary reactions at equilibrium that we can use this. So let's look at a slightly more complicated reaction and how we can apply this and how we can get back to sort of the same sort of setup. So let's look at a reaction with that's between A and B, right? So this is the complex reaction. And we can consider a reaction mechanism that has two possibilities. So we can have either A reacts with a catalyst, C, so it's not actually part of the equation, and goes to B plus C, so the catalyst is unchanged, and that can go in the forward and reverse directions. So that's our step one of our mechanism. And the other option is to have no catalyst. A just directly goes to B, and of course this can also go in the reverse direction. So the difference between step one and step two is that it can happen with a catalyst or without a catalyst, and that's our mechanism. And so one thing we can recognize here is that if this complex reaction is at equilibrium, then all of the steps, all the mechanism, all the elementary steps of the reaction also have to be at equilibrium. Because if they're not at equilibrium, right, if the rates are not the same, then there is a net change in the concentrations of products or reactants, right? If the forward and reverse rates of our elementary steps that make up the mechanism are not at equilibrium, that means the overall reaction can't be at equilibrium. So if we reach equilibrium, we can say that all the steps have to be at equilibrium as well. And so we can derive relationships between K1 and K minus 1 and the equilibrium constant. And what we'll see is that we get, I'm skipping some steps here, but we can use the same sort of analysis we used in the previous question to get the fact that Kc will be equal to K1 over K minus 1, or it'll be equal to K2 over K minus 2. Right, both of these will be true. Because in the case of our first step with the catalyst, even though the catalyst shows up, the catalyst will show up in the rate law. Because it shows up in both the forward and reverse directions, it cancels out and doesn't show up in that equilibrium constant expression. And for the second step, it's basically the exact same thing we just looked at for the original example that didn't have the catalyzed reaction as a possibility. One additional thing we can do here is look at what is the for this reaction, show that the equilibrium condition gives us overall that, oh, that's where I'm going with this, that overall we can also say that another way of expressing this, there, let me put it this way, is that all of our forward reaction rates have to be equal, the sum of the forward reaction rates have to be equal to the reverse reaction rates as well. So we'll probably do this in class, or I'll have you do this on your own. Show that from this expression here, we can also get back to this original, this expression here, that the equilibrium constant is equal to the forward and reverse, to the rate constants of the forward and reverse reactions divided by each other. And so this, I guess, one thing I just want to point out is that we can write rate laws for each of these steps. For V1, V2, because this is a key idea in analyzing reaction mechanisms, is to be able to write the rate laws for each step. So for V1, we can write that it's K1 times A times C. V2 is K2 times A. V minus 1 is K minus 1 times B times C. And V minus 2 is K minus 2 times B. And so we can get these directly from what the forms of the elementary steps look like. And then we can plug these into this equation, and this is an exercise I'll leave to you, but show that when you plug all these in at equilibrium, specifically, right, when you use the equilibrium concentrations for everything, you'll get this relationship again, that the rate law, that the rate constants, the ratio of them is equal to the equilibrium constant. And the key to doing this is to eliminate C equilibrium from your equation. And so this is example 29-2, and so I encourage you to look at that in your textbook. But that is where I'll stop this video.